Right, the first question for this is pretty much right out of a previous tutorial. We're finding the null space, the column space. The addition to that is the rank of A and the dimension of the null space of A respectively. So it's just dimension and the rank that is added onto this question. So as previously, we're just going to look at the transformation. Where's it going? T is going from V to W. If this is the case, we have the kernel of T is a subspace of V, range of T is a subspace of W, where kernel of T is a subspace of R5 in this case. Right, we can use these pieces to figure out what to look at. So find a basis for the null space of A. Since both questions are asking for the kernel range, null space, whatever, I can just use my previous solution. It's pretty much the exact same. But anyways, kernel of T implies that we're going to have our T of X is equal to 0, which implies that AX equals 0 because T goes to A here, right? Which by definition is going to be the null space of A. Right, we have the null space of some matrix goes to that matrix equal to 0. So the null space of A is just going to be A equals 0. We have this matrix up here. First we want to see if we can row reduce, because that's just going to simplify our solution set. We see that we can, so we get our REF. After that, we note our free variables as done previously. Set those equal to some parameter variables. DKP, element sum field. Therefore, the null space of A is equal to our column 1, column 2, column 3, column 4, column 5 solutions, x1, x2, x3, x4, x5 equals this. We're going to move everything over to the right. Free variables are just going to be free variables themselves, so we don't have to move them over or anything. Then we're going to want to split this up. We have TKP, so TKP, find those pieces, define them to be an element of some field. And then when we take the span, we're just going to write out our T, our K, and our P vectors. And what's the additional piece to this question? For the null space A and a basis, right? So if we want to check that this is a basis, we want to say, is this linearly independent? And we're going to see that we cannot craft the first vector from the second one, or the third one, or any combination. Similarly, we cannot do this for the middle or the right side, right? Because we have a 1 here, a 1 here, a 1 here. We have a 0, 0, 0, 0, 0, 0. We cannot take any multiple or addition of them. So we can say that these are all linearly independent. If you wanted to check, you can just set up a matrix and then REF. Okay, and then what's the next one? A basis of the column space. Right, so we have the range of T is a subspace of R3. So that means the column space of A is equal to the span. We just take the columns of our A. Since it's asking for a basis, what we can do is we can just note the pivot points for our REF of our null space over here. So the first column, the second column, so we can just take those columns themselves, because what that's going to imply is that they're going to be linearly independent, because we're going to have the pivots run along the diagonal, right? So everything below that's going to be 0, 0, 0, 0, 0, 0, 0, which means we cannot take any combination. Right, so that's linearly independent. And what's the next thing it's asking? Find the rank of A and the dimension of the null space of A. Right, so note the basis, the column space A, take pivot columns. I noted that down here, okay. Non-pivot implies free variables, implies linearly dependent, implies not a basis. Yep. So the dimension of our null space is equal to 3, and the dimension of the column space of A is equal to the rank, which in this case is just going to be 2 vectors, so it's just going to be 2. We can note that the rank plus nullity is equal to 5, which is equal to another column, so that works out. What is B? A basis of the kernel of T, basis of the range of T, respectively. Find the nullity and rank of T. So here we can just note that the kernel of T is equal to the null space, as we did up here, right? Range of T is equal to the column space, as we did over here. Therefore, just the dimension of the rank of the nullity is basically just going to be the same thing as this, right? So dim kernel T, which goes to the null space, is going to be the nullity. Since we define that up here to be 3, that's also going to be 3. And the dimension of the range of T is just going to be the dimension of the column space of A, which is going to be the rank, which is going to be equal to 2. And I think that's it for that. Yeah, you can just leave it as a kernel T equals null of A. You don't have to write out the basis again if you want. Okay, what is 2? Let P2 be the vector space of all real polynomials with degree at most 2, and T be a linear operator of P2 defined by Tpx equals x times the derivative of P, where P is the derivative. Okay, they just said it again. Anyways, to start this, we're going to want to define some P2 polynomial, right? Because this is what the question is wondering about. And it's all real polynomials with degree at most 2, right? So this would be inclusive of all, because if we did not include all of our coefficients, then we can't possibly generate all. So we take all. P2, once again, is just up to degree number 2 with a constant first degree, second degree. And we would find our leading coefficients to just be an element of some field. From the definition of how we define the transformation, we're just going to say that P2, based on this piece up here, is going to be equal to the set of x times p derivative 2. Since this is our P2 up here, the derivative is just going to be the power rule. So once we do that, and then we multiply by x, we're going to get a1x plus 2a2x squared. We define it once again to be an element of the field, as we did up here. We carry that down. So now we start with the first question. Find a basis for the range of t, which is just going to be the polynomial itself in some space, some P2 space. Right, so if we have a1 plus 2a2x from our setup here, that means that the range is going to just be equal to the span of x 2x squared. And it's very important that we keep the 2, because say that this was an element of integers. Right? If it were the case that there was an element of the integers, then we would include only even numbers, right? 2 times 1, 2 times 2, 2 times 3, 2 times 4. Basically, even times odd, even times even just goes to even. So if we left out the 2, then we would get odd solutions when that did not originally exist. So just make sure that you keep the 2 there. And we're going to define this to just be x is going to correspond to a1, 2x squared is going to correspond to a2, as we do over here. So that's how you would translate it into a span. You can also go backwards, which is precisely why I defined it up here. Right, so our span is linearly independent, right? We cannot take an x and get an x squared. That's just not possible. We also can't get x squared from x. And so it forms a basis of the range. Okay, what's the next one? Find a basis for the kernel of t. So this is just going to be to tpt, which is equal to x p derivative 2 equals 0. Right? In this case, we always set the transformation equal to 0. So we take the resulting transformation, set that equal to 0. So we get a1x plus a2x squared equals 0. By grouping and coefficients, it's only possible if we have a1 and a2 equal to 0 both. We're going to take these values and actually sub them back into our original set over here. It's very important that you do that. So once we do that, we're just going to get a0 plus a1x plus a2x squared. But since these are equal to 0, we're just going to get rid of them like this. Define it once again to be an element of the field. Therefore, once we take the span, right, we're just going to take the coefficient out. Therefore, equals span, element of 1. So our span is linearly independent, and so it forms a basis of the kernel of t. Right? This is linearly independent, it's just one element. What is C? Find the rank and nullity of t and give a formula relating the dimension of P2 and the rank and the nullity of t. Okay, so once again from the first question, right, we're just using the definition. Rank is just going to be equal to the dimension of the range of t, which in this case, we're going to look up here, we see that it's 2. And the nullity is just going to be equal to the dimension of the kernel of t, which from here is going to be 1. And for our note, we're going to say that the dimension of the kernel of t plus the dimension of the range of t to the nullity and the rank equals dim P2. Right, so I'd say this is rank, this is nullity, so this is the piece that we wanted to find. So that's it. Okay, question 3. So there are 2 ways to do this. One way is just faster, but let b equals the set 1 plus t, 1 plus t cubed squared, t plus t squared. I'm not speaking well today, I'm sorry. Be a subset of P2. Justify that B is a basis for P2. So the first method you could do is just convert it immediately to a coordinate vector with respect to, say, a P2 polynomial space. So what it looks like is C t squared. That satisfies all of P2. Take each vector in here and convert it to its column space form like this. After you do that, you're going to form it as a matrix going from right to left, or left to right. So once you get this, you're going to REF. What you want to note is that we have no free variables here. That's very important because now we can convert it back to the original one. After we do that, we get B equals the span 1, 0, 0, 0, 1, 0, 0, 0, 1, which obviously covers everything in there. We have our C, we have our T, we have our T squared. Right, so that covers all of our P2. So now we note, since dim B equals dim P2, where B spans P2, as I set up here, and all vectors are linearly independent, right? We cannot take any combination of these to form any of the other ones, and there are no free variables. You can use this. Everything will be linearly independent if we have no free variables, which is why this method is just faster. So we have B as a basis for P2, based on this piece. Method 2 is the other one, which is more annoying, but you take some arbitrary scalars for all your vectors, C1 V1 plus C2 V2 plus C3 V3 equals 0. Sub in your V vectors. After you do that, you're going to distribute your scalars in, then you're going to group for constants, first degree, second degree. Then you'll set up the matrix. And you'll notice that we actually just get the same result as up here, right? So it's just skipping all this. So I would do this if you can. Unless it says that you shouldn't do this. I'm okay with you guys doing this, but but yeah, take the REF. We get once again 1, 0, 0, 0, 1, 0, 0, 0, 1. The no free variables. In this case, we would say that C1, C2, C3 equals 0. So all of our C's equals 0. This is just the same thing as saying no free variables, which implies that this is a linearly independent set of 3 vectors. Right, since we have dim P2 is equal to 3, that's not a very good 3. We have B as a basis for P2 as it covers all this and it spans. Okay, number 4. This is a linearly independent set of vectors in a vector space V is a basis of the subspace it spans. I mean, I think most of these are just definitions. Yeah, true by definition. So if T is a linear transformation from V to W, and V1, V2, Vn are linearly dependent vectors in V, then T, V1, V2, Vn are linearly dependent vectors in W, and this is just the proof there. And so if our vectors are linearly dependent vectors, then there exist scalars not all equal to 0, such that C1, V1, equals 0. So we apply T to both sides of the equation. We have the scalar of our transformations equal to 0. Since the scalars are not all equal to 0, because that follows from the first result up here, this will not change that. These are linearly dependent vectors in W as the transformation takes these vectors and translates them to W. Okay. What's this one? C, if T is an invertible linear transformation from V to W, then dim W equals dim V. I think these are all just in the lecture notes. But yeah, we say that's true. Dim kernel T plus dim TV equals 0. Right, so then we get, equals 0 plus dim W equals dim V. What's D? Let M and N are subspaces of a finite dimensional vector space V. The dim M plus N equals dim M plus dim N minus dim M intersection N. Once again, this is true. Oh yeah, I wrote this down. You can just find that on page 19 for notes 3. We just have dim M plus N plus dim M and N equals dim M plus dim N. There's a lot of dims, I'm saying. Dim sum. Okay. What is this? 1, 1 is the only eigenvector of the matrix 1, 2, 2, 1, corresponding to the eigenvalue 3. We say this is false, and I gave a little example here. So consider some scalar C for our eigenvector 1, 1. That is C times eigenvector 1, 1 goes to C. Then check for lambda equals 3. The way we check is we take our A, we multiply it by our lambda. So in this case, we get 1, 2, 2, 1 times our CC equals 3C, 3C. And we know that we can factor out 3 from here, which is going to be our eigenvalue. So therefore, from this definition that we've defined C to be any non-zero scalar, that gives us that our eigenvector 1, 1 for any scalar that is non-zero can be said to have an eigenvalue of 3 as well, because we can factor 3 out. So therefore, not the only eigenvector, right? So it's not unique, and that'll just make it false.